So let's keep going. So what do I think the difference is? So to do this, let's dig in a little bit. I think the way I think about estimation is everything you'll ever see that's an estimator is about a black box that takes a data set. Let's walk through this step by step. The data set is a bunch of y variables and x variables. They're assumed to be IID. You kind of need that. And then some function class. For example, OLS says linear functions. It takes that in, and then it outputs the function that it's estimating with a confidence interval. For example, with OLS, it would say, this is my coefficient vector. This is my confidence intervals on that coefficient vector. And what estimation and all of estimation really builds up to, so for example, the fact that OLS is blue is the idea that it's an unbiased estimate of the truth. Meaning, when the data is being generated by a linear function, my estimator is going to find that right function on average. It's a consistent estimator. Does that make sense to you guys? This is roughly what all of estimation does. Now, this is not causal yet. This is not even at the level. That's the thing is, people always say, oh, machine learning is not causality. Forget causality. We're just literally talking about the most basic feature of estimation, consistency. You can get a consistent estimator, and it's still just a correlation, not a causal inference problem. But it's just saying at least you're getting the right coefficient for the variables you have. Does that make sense to everybody? OK. So this would be face data. These would be rectangle features. And here would be my face predictor. That's what would be coming out. Now you already see kind of the problem that's going in. Like, the data set that's going in is the information that's coming into this little black box, thousands of data points. The thing that's coming out is a face predictor, which means it's a function on, let's say, 144,000 things, which means I'm getting hundreds of thousands of coefficients out. How am I taking 1,000 data points and getting hundreds of it fails the most basic counting exercise you would do in math. So how can we be getting more information than we're putting in? The key is we're not. This is not what these algorithms are doing. This is what an estimator does. These algorithms correctly recognize, why do we need this? I never said I was estimating the right coefficients for some face predictor. I'm in no way or shape or form trying to get the right coefficients. Instead, all I'm doing, if you recall, is just to get a function that works well at predicting. I only need good predictions. I've never told you I was getting in any way consistent estimates of the coefficients. And if you look at all these tasks, they have all that. They have exactly that feature. I am not attempting to find the coefficient. I never said to you, oh, now we found the coefficients on the word, job in a positive movie review, negative review. I just said, I have this thing. It takes all of it in, and it does pretty well at predicting things. So in a way, if you were to write down this stuff, estimation is about getting the right F star. Prediction is about getting unbiased prediction quality. That is, you're doing pretty well at predicting something. I think this distinction is super helpful, which is now when you put it this way, you say, oh, look, estimators at least get you the right function. But they don't get more out because they have to assume low dimensionality. And now you start to see the tension between these two. And if I were to put it even simpler, I'd say estimation, which is what we often spend our time doing, we make strict assumptions about the data generating process, but in turn, we can back out coefficients. We live in a low dimensional world, we're getting good coefficients. Prediction, we're allowing for very flexible functional forms, and we get high quality predictions, but we do not get coefficients that are meaningful. This is low dimensional, but we give up on adjudicating between observably similar functions. This is beta hat, this is y hat. So if I were to try and think of the big distinction you could carry around in the back of your head, it would be sometimes we really care about betas. That's the low dimensional world. That's the world where a lot of the estimators you're doing. Sometimes you say, I just want whatever the x is, a y hat that works pretty well. And if you look at all the examples that come out of machine intelligence, they don't tell you what's inside the black box. It's that the y hats work pretty well. And sometimes that's what you care about. So I think for me, I spent a long time on this and finally came to this slide, which was gee, I understand beta hat is a very, very different object than y hat. And the biggest mistakes I've seen are people using predictors and looking inside and saying, isn't it funny that it uses this thing? What does that mean? It means nothing. Don't look under the hood. Or people taking a y hat problem and saying, let me run estimation on it. Why? You only cared about y hat. Why are you restricting yourself to this silly low-dimensional class? It's a prediction problem. Turn it into a y hat problem. Did you have a?
Yeah, so if we take a limit, right, of prediction, would it approach estimation? Because like if estimation gives you the true coefficient, and like the true coefficient would give you the actual value. Whereas with y, we're sacrificing a bit of that for just the sake of making.
Yeah.
Like if prediction gets good enough,
Great.
to get the data.
Great question. Yeah, so let's maybe just, I have slides on this that I can load up. I'll try to do this just on the chalkboard too.